In this screencast, we will be performing bubble point and dew point calculations using Raoult's law. We have data in the form of a graph of the vapor pressure of both component A and B. If we didn't have this kind of chart, we could find the vapor pressure of A and B using an equation like the Antoine equation or something similar. First question simply asks which component is more volatile, A or B, and how do you know that? Well, if we look at the graph, we can see that the vapor pressure of component B is always higher than component A. Therefore, component B is more volatile. So component B, and it's a normal boiling point for B, and they want to know is it less than 30, between 30 and 40, 40 and 50, or greater than 50. At the normal boiling point, the vapor pressure will be equal to 1 atmosphere pressure, which is about 101 kilopascals. We note that even at 50 degrees C, the vapor pressure of component B is only about 24 kilopascals. Therefore, the normal boiling point will certainly be larger than 50. In the next question, we've got B alone in a container, where we know the pressure, and we're asked, what is the temperature? Well, since B is in both the liquid and the vapor phase, we can write Raoult's law for that. So the vapor pressure is just equal to the total pressure. So with a vapor pressure of B, we can go up and find the temperature for B. It's like about 41 degrees Celsius. Again, B is present in both the vapor and the liquid phase. Right, Raoult's law. And YV turns out to be about 14% mole percent. And we're going to draw a picture. We're looking for the pressure where there's just the first drop. This is called the dew point pressure. We know that nitrogen's not going to condense out, so XA here is just going to be 1. So again, writing Raoult's law on A, because it's present in both phases. Simplify. At 50 degrees, A has a vapor pressure of about 12. Fairly high pressure, but A is only a minor component in the vapor phase, therefore it takes quite a bit of pressure to get to the dew point. This is a conceptual question about Raoult's law. You have vapor and liquid system with only A and B. If A and B form an ideal solution that is valid for both A and B for all compositions. This is kind of the definition of an ideal solution, so it is definitely true. For a vapor-liquid system of only A and B, if A and B do not form an ideal solution, but the mole fraction of B is very small, close to 0, Raoult's law will be valid for component B. Well, that is not true because B is feeling mostly the effects of A, and since it's a non-ideal solution, we may be able to use Henry's law for component B, but we would not use Raoult's law. However, for number 3, we have a A and B system. Again, they don't form an ideal solution, but the mole fraction of B and the mole fraction of B is very small. Raoult's law will be valid for component A, and this is true. Component A really does not feel the effects of component B, so component A you can still use Raoult's law on. For a vapor-liquid system of A and I, Raoult's law will be valid for A, but not I, and again, that is true. We're only having one. That's the application we were using previously. And if A and B are molecularly very similar, it is likely that Raoult's law will apply over the entire composition range. And this is true because if they're molecularly similar, they will likely form an ideal solution where the A interactions and the AB interactions and the BB interactions are all the same. We'll have A and B in both the liquid and the vapor phase, so we'll write Raoult's law for both phases. We know the mole fraction in the vapor phase of both A and B. The one that we don't know is XA and XB. Since we don't know this, the easiest way to solve this system is to write down the mole fractions, the statement that the mole fractions in the liquid phase add to 1. This makes our third equation. We'll solve for both XA and XB in these equations, and substitute it into the statement of the mole fractions equaling 1. This is very nice because we only have one unknown. We've eliminated the XA and XB unknowns. We only have one unknown in this equation, and that is P. So it's just a matter of solving for P. We don't know the vapor pressure of A and B, but we can certainly get it because we know the temperature. So that's just a matter of looking up on the chart what those are. We are given A and B, so then we can solve for P. Once we have P, then we can use these equations here to solve for the composition of the liquid phase. So we can see that the pressure is 11 kilopascals and that the mole fraction of A in the liquid is 0.47. So now it says include a statement of reflection. So we're going to try and put this in context and see if the numbers make sense at all. A pressure of 11 kilopascals is between the vapor pressure of A and B. We also have that the mole fraction of A is larger in the liquid phase than it is in the vapor phase. And this makes sense also because we said before that A is the least volatile component, so it would favor the liquid phase. So both of these seem to make sense. We also can say that we would have to increase the pressure to 11 kilopascals to form the first drop of liquid. If we were any lower pressure than 11 kilopascals, we would have all vapor. Moving on to the next question, we set it up the same way. Most of these equilibrium type questions, you can draw a simple diagram. That is very important to do to give you an idea of how to solve the problem. It's very important in a problem-solving technique to have a simple diagram. And now we're looking for the bubble point pressure. That's where the first bit of vapor will form. We have mostly liquid. Just write down our information that we know from the problem. Again, we have the same Raoult's law for both A and B because we will have A and B both in the liquid and the vapor phase. Now we will use the fact that for our third equation that the sum of the mole fractions in the vapor phase is we do not know the composition of the vapor, and so that's the equation we want to write. Again, we'll solve for y and yb in these two equations and substitute in, or just the pressure is just, we have the same temperature, so we're going to have the same vapor pressure as in the previous part of the vapor pressure of A being 7 and B at 14.2. And again, we'll use the again, we want to reflect on these answers. The pressure here, 12 kilopascals, slightly larger than 11 kilopascals. We had the same composition. The overall composition stayed the same. The temperature stayed the same, but the bubble point pressure was a little bit higher than the dew point pressure. And if you think about it for a little bit, that would make sense. We'd need a higher pressure to all into the liquid phase. Again, A is the least volatile component, so it makes sense that the composition in the liquid phase would be higher than the vapor phase. So that would, our statement of reflection should include that, and also that the pressure is between the vapor pressure of both B and A, so that also gives us those we're within those limits. Now we have a non-ideal solution, but looks like in the liquid phase we have predominantly B. So while we can't write Raoult's law for A, B is at 99%, so we can probably get away with writing Raoult's law for B. Here we know the pressure, 100 kilopascals. We also know XB and YB. So the only thing we don't know is the vapor pressure of B, which is really only a function of temperature. So we're going to solve for the vapor pressure of B, and then we will look on our chart for the correct temperature. And the temperature is just a little over 41. This makes sense because the partial pressure, this value of YB times P, or B's contribution to the total pressure, is about 15 kilopascals. So since B is mostly, the liquid is almost pure B, we could see that the vapor pressure of B would have to be close to 15, which gives us that temperature of around 41 degrees. So this also seems to make sense, and that would be included on our reflection. So, come to the end of this practice quiz, where we have explored using Raoult's law on a component of A and B under different conditions. And again, one of the big factors in solving these problems is setting up a simple drawing of the system, identifying the knowns and the unknown, and simplifying the equation